Hey everyone, Mrs. Ragstad here. This is video 10.4 on Newton's laws, and in this video you will learn in further detail what the three laws are, and in particular you will learn how to solve Newton's second law with actual problems. So let's recap. Sir Isaac Newton put together three comprehensive laws that explain how things work in the world of physics, how things move. So Newton's first law in long form states objects in motion tend to stay in motion and objects at rest tend to stay at rest unless acted on by an outside force. This is also known as the law of inertia, and that word is written right here. So what inertia means is resistance to change in motion. So if you're feeling like sluggish and you don't want to do stuff, you are experiencing inertia. But in the world of physics, where we're just talking about objects that are moving, not necessarily human behavior, inertia has to do with mass. So the more mass something has, the more inertia it has. The less mass something has, the less inertia. So if you want to consider those big boulders that are out on Eagle Park where some people like to sit at lunch, they are really, really big and really heavy. If you tried to apply a force to one of those, it probably wouldn't move. You'd probably need a lot more force, maybe a bulldozer or something like that. And so those boulders have a lot of inertia. It has to do with mass. Something that has very little inertia would maybe be a ping pong ball or something that is very light, or like this crumpled up piece of paper that I showed you in a previous video. It's very little inertia, easy to apply a force and it will move. Now, I'm going to take this time to explain the difference between mass and weight, because mass is what gives you inertia. The more mass something has, the more resistance to change in motion. And I'm going to write that right here. Resistance to change in motion. Meaning it takes a lot more force to move something with a lot of inertia. And that's what mass is. Now, this is sort of related to the concept of weight. So when we say like, oh, how heavy is something? How much does it weigh? But in the case of weight, we're talking about the mass in the presence of gravity. Okay, so this really has to do with behavior under gravity. Which is why when we weigh a person, we stand on a scale, and that is determining the behavior of your mass in the gravity of Earth, because you are being pulled down on the scale. The spring inside the scale is depressing, and that is what the instrument is measuring. On the other hand, in our class, we use a balance. We use a triple beam balance that works like this, where you put the object you're trying to determine its mass on this side, and on the other side, you have the sliding weights or masses that of known mass, and when the two are balanced, you have determined this mass compared to this mass, and it's pretty much independent of gravity, even though we need gravity to figure it out, because you're comparing this mass to this mass on the balance. You're not depressing a spring in the presence of Earth's gravity. So this is why when we're talking about weight, different objects, their weight will change on Earth versus on the moon, or on Earth versus in outer space. So say a person weighs 150 pounds on Earth, that person is going to weigh 1/6 of 150 on the moon, because the moon's gravity is so much less, because the moon itself is a smaller body. It's not a planet, it's a moon, but you get what I'm saying. And in outer space, if somebody goes out to live on the International Space Station, that's what we call an environment of microgravity, because it's like they're constantly falling towards the Earth, and then the Earth moves away. And so they experience weightlessness. However, the mass of this person, say they weigh 150 pounds, on the Earth, on the moon, and in the International Space Station, their mass is constant. And we can measure mass in kilograms. Their mass doesn't change. They have the same resistance to change in motion, the same resistance to force. It's just that their resistance to force under different gravity is what weight is. So that's a difference between weight and mass that I want you to be able to explain. Weight is how masses behave under gravity. Mass is resistance to change in motion across the board, no matter what gravity you're under. All right, so that's Newton's first law. I've already explained Newton's third law in a different video. For every action force, there's an equal and opposite reaction force. So if I am pressing on this table right here, the table is pressing back up at me. I am sitting on this chair, I'm putting a force on the chair is putting a force on me. If I lean over here and touch this wall, I'm putting a force on the wall, but the wall is also putting the equal and opposite force back on me. If it weren't, I would fall into the next room. All right, so now we're going to spend most of this video focusing on Newton's second law, which is force equals mass times acceleration, and I'm going to show you how to solve some problems along these lines. All right, so here's our first problem, and this is from your textbook in section 10.4. It says a car with a mass of 35 grams accelerates down a hill at a rate of 6.13 meters per second squared. Determine the force causing this acceleration. So our procedure is the same as it always has been, except we're dealing with a new equation now, which is Newton's second law. And with Newton's second law, there's some things with the units we'll have to look at. So I will explain that as we work through this problem. But let's just start at the beginning like we always do. So our knowns, we have a mass of 35 grams, and we have an acceleration, and we know it's acceleration because it's meters per second squared, of 6.13 meters per second squared. And our unknown is force, and it does not tell us the units. So when we are dealing with force, these are the units you always use. Units of force are called newtons, and that's represented by the capital N. It stands for newtons, named after Sir Isaac Newton. Isn't that cool to have a unit named after you? Something we should aspire to. And a newton has a definition. So it's a complex unit that is made up of other units. So I'm going to write that down here. 1 newton equals 1 kilogram times meters over seconds squared. Okay, so you can see that these are the units. 1 newton equals 1 kilogram times meter per second squared. So when we're comparing our known and unknown units, we know that this needs to be in newtons. And if you would like to write what a newton equals for the purpose of comparison, that might be helpful. This way you can compare your knowns and unknowns. Okay, so we have a mass in grams. I need it in kilograms, so that's going to need to be converted. I have an acceleration in meters per second squared, and right over here, meters over second squared, that is good. I don't need to change that. I only need to change my grams into kilograms. So I'm going to do my parentheses right here, do my unit conversion. Grams is on the top, so it goes on the bottom. I'm converting to kilograms, and then you need to ask yourself how many grams are in a kilogram. And if we remember, way back, we have the King Henry died by drinking chocolate milk. This is kilo, hecto, deca, base unit, deci, centi, milli. Okay, so gram is the base unit. Kilo is way over here. So we're looking at 1, 2, 3 spaces. So we know it's going to be 1,000 times because 1,000 has 3 zeros. The question is which way. So which one is smaller, a gram or a kilogram? And the answer is a gram is smaller. Therefore, there are 1,000 grams in 1 kilogram. And to give you an idea, a hydro flask that's filled with water weighs about a kilogram, or has a mass of about a kilogram. A gram is probably the mass of like a paper clip, maybe 2 paper clips. So that gives you a sense of the difference in mass. Okay, now because the 1,000 is in the denominator, we're going to divide. So 35 divided by 1,000 means I'm going to be moving my decimal place 3 spaces to the left. That's going to be 0.035 kilograms. So that's it for unit conversion, because I have kilogram and then meters per second squared. So all I need to do next is write the equation, and Newton's second law is force equals mass times acceleration. And then step 4 is substitute and solve. Force equals 0.035 kilograms times my acceleration is 6.13 meters per second squared. And then I just put that in my calculator and I will have an answer. 0.035 times 6.13 equals 0.21, and you can round at this point. 0.21 newtons. And that's your answer. Now, there could be other problems that you encounter where you're solving for acceleration instead of mass. And in those cases, we can start with F equals ma. But then if we're solving for acceleration, we want to isolate the acceleration. So I can divide both sides by m and end up with A equals force divided by mass. So that's another version of this equation that you may need to use in a future problem. All right, that's all I have for this video. Have a fantastic day.